Today's notes are on areas in the plane. So if we want to find an area of a curve or the area between two curves, we can take an integral, which we kind of already know. Um, but one thing that we touched on a little bit earlier that we haven't really fully got into is that if we have problems such as these three visual examples that we have, so for example, the first one is the area between y equals x squared and y equals 4 from 0 to 2. So if we're trying to find the area from x is 0 to 2, what we used to be able to do is we could find the area of this rectangle, which was 8, and then subtract the area under the curve, which was the integral from 0 to 2 of x squared dx. We could do that and we would end up with the answer. But what we also can understand about this problem is that if we just only want to find the shaded area, what we could do is we could take the integral of y equals 4 from 0 to 2 and subtract the integral from 0 to 2 of y equals x squared, and we end up with the exact same thing, which is 8 minus the integral of 0 to 2 of x squared dx. That's identical. Now, what we learn up here from our integral rules is that if we subtract those two integrals, we can actually write it as one integral. So I could write this as the integral from 0 to 2 of 4 minus x squared dx. And so what we're going to end up doing in this chapter is, or in this section, is we're going to end up finding the area between two curves. Looking at the second example, this is y equals negative x squared plus 6 and y equals negative 2. What we used to be able to do was find the area under this by just integrating the first curve and then adding it to this integral, or adding it to the negative of that integral because it's underneath the x-axis, and we would have been able to do that. Or we could have done a vertical shift where we move the entire graph up 2 and then treated it like it was y equals negative x squared plus 8, and then integrated that from x equals negative 2 to 2. But what I am now saying is that we can take this problem and write it as the integral from negative 2 to 2, so no, or not negative 2 to 2, sorry. We can write it as the integral from these 2 points, which we would have to solve for. And so if we solved y equals negative x squared plus 6 and set that equal to negative 2, we would find out that x squared equals 8. So we would not have negative 2 to 2. We would have negative root 8 to root 8. So that's my fault on that. So we take the integral from negative root 8 to root 8 of the bigger curve, which is negative x squared plus 6, and subtract it from the smaller curve, which is negative 2 dx. And we could simplify this to be negative x squared plus 8 dx. Notice that that's exactly what happens if I did a vertical shift of 2 here. I would end up getting negative x squared plus 8. And my intercepts would be at negative root 8 and root 8. Finally, if I have the same parabola, but the line y equals x plus 3, or 3 plus x, since I ran out of room to write it, what I would have to do is I would have to once again find these two intersections. What I used to have to do is find the first integral, which would be this whole thing, and then subtract the part underneath the line, and then that would leave me with just the part that's only blue, that's in this this like pink shaded region here. But now what we can do is we can just take the integral of the top curve minus the bottom curve. So I will find this. I'm going to call this point A comma B and this point C comma D. If we were actually doing this for sure, you would have to actually find those values. But I can take the integral from A to C of those two things, and I'm going to take the top curve, which is negative x squared plus 6, and subtract the bottom curve, which is x plus 3. And that will actually give me the integral of this shaded region, or the area of that shaded region. So in order to find the area between two curves, we can simply take one integral as long as we set it up carefully. We usually have to have a good graph, and what we end up with is the integral from the lower bound to the upper bound. And if we're doing this with x's, those are going to be the x values. Integral of the lower bound to the upper bound of the top curve minus the bottom curve dx. So let's take a look at number 1. Find the area of the region between y equals secant squared x and y equals sine x from x equals negative pi over 4 to pi over 4. So if we take a look at a graph of this, sine of x is just like secant's reciprocal, basically. So, I'm sorry, secant is just like cosine's reciprocal. I don't know what I was talking about. So secant is cosine's reciprocal. So if I have secant squared between negative pi over 4 and pi over 4, that's going to be looking something like this. It's between these two values. And then if I take a look at the sine graph from negative pi over 4 to pi over 4, remember the sine graph looks something like this. But it should go all the way up to 1. And notice if this is secant squared, that's 1. So it should go something like this. So if I have pi over 4 and negative pi over 4 as my outlooks, this should be the area that I'm kind of looking for. If I actually graph it a little bit better than my freehand sketch, it will look something like this. So I want to find this area in here. And what I can do is I can take the integral of these two functions from negative pi over 4 to pi over 4. That's my lower bound and my upper bound of the top curve, which is secant squared of x, minus the bottom curve, which is sine of x, dx. This is a problem I can do without a calculator because the integral of secant squared, an antiderivative of secant squared, is tangent, and an antiderivative of negative sine is cosine. So I can take this and I can evaluate it from negative pi over 4 to pi over 4. If I substitute values in, I get tangent of pi over 4 is 1. Cosine of pi over 4 is root 2 over 2. And then I'm going to subtract what happens when I plug in negative pi over 4. So that's minus negative 1 plus root 2 over 2. So I have 1 plus 1, and then the root 2 over 2's cancel. So I end up with this integral equaling 2. Now let's take a look at problem 2. Find the area of the region enclosed by root x, x minus 2, and the x-axis. So if I take a look at this problem, square root of x looks something like this. X minus 2 looks something like this. They should probably intersect here if I actually drew this moderately correctly. So I would have a slope of 1, and it intersects at 4 comma 2. And I'm looking for this shaded region. Notice that it does not go below the x-axis. It says that it's also bounded by the x-axis. So that is a bound. Now, once again, that was a really not so necessarily quality picture there. So if I get a little bit better picture, and you will be expected to have quality pictures. Uh, if you are not given a picture, and on the AP test, it's possible that they won't give you a picture. Uh, so this is the region that we're looking for. Now, one thing that you're going to notice about this region is that uh, it's not a clean region. And what I mean by that is our general form is lower bound to upper bound. So the integral from lower bound to upper bound of top curve minus bottom curve dx. Well, the issue with that is at 2, we change what the bottom curve is. So notice that from 2 to 4 for the x values, the bottom curve is y equals x minus 2. However, from 0 to 2, the bottom curve is the x-axis, which is the line y equals 0. So we actually have to break this up into two separate integrals in order to do this problem. So the integral from 0 to 2, so that's lower bound to upper bound of this blue region, that's going to be the square root of x dx. We could also write it as square root of x minus 0. And the reason why we could do that is because the bottom curve is the line y equals 0. So that's something that you might want to be aware of. Now we're going to add that to the red region, which is the integral from 2 to 4 of the top curve, which is once again the square root of x, minus the bottom curve, which is the line x minus 2 dx. And so when we do this, we have 2/3 x to the 3 halves, and that's evaluated from 0 to 2. And then I'm going to add it to 2/3 x to the 3 halves, evaluated from, I'm sorry, minus 1/2 x squared plus 2x, and that's evaluated from 2 to 4. So notice I could have distributed the negative sign, and that's why the signs end up being the way they are. So when I do all of this, I end up getting 2 root 8 over 3 plus 16/3. And then I get, sorry, the plus 16/3 is red, my fault. So that's the first part, 2 root 8 over 3, and then when I sub in 0, I get 0. So plus 16/3 minus 8 plus 8. Then when I sub in 2 over here, I get minus 2 root 8 over 3 because I have to subtract everything. Minus 2 root 8 over 3 plus 2 minus 4. And so when I do all of this, a bunch of stuff cancels out, and I end up with 10/3. So notice these cancel out. These cancel out. I get 16/3 plus 2 minus 4, which ends up being 10/3, or 3 and 2/3. So that's the area of the blue plus the red, which is the entire shaded region that I wanted. On the back, we're going to repeat the previous problem using another method. Now, I haven't taught you another method yet, but what I'm going to do here is, if I take this exact same situation that I had, if I have a picture that looks something like this, what I can do instead is, instead of having this break up here, and I have two separate regions that are done in terms of x, where I'm doing all of these little vertical rectangles that I had when we learned Riemann sums. Instead, what I can do is I can take a bunch of little horizontal rectangles and find these areas. And so I can do little um, little horizontal shaped rectangles where the change is really small in terms of y. So pretty much everything we've ever done so far has been these integrals of something, something, something dx. And that's when we had really very small changes in x. But if I do it the other way, I can have changes in y, little dy's. So I could also have an integral with something, something, something dy. This makes our life a whole lot easier in a problem like this, because if we look at this problem, if we take integrals with little rectangles going in the opposite direction, notice that we have only one region that we have to deal with. In the previous situation, where we could only deal with dx, we had to separate this into two separate integrals because we had a top minus a bottom, and that bottom function changed. Whereas here, if we're going from right minus left, the right function, which is that red line, never changes, and the left function, which is the black curve, never changes. So if I change these functions to be in terms of y, I can square both sides, and I get x equals y squared as one function, and add 2 to the other side in the line, and I get x equals y plus 2 as my other function. So if I take a look at this, the red function, which is my right function, is y plus 2, and my black curve, which is the sideways parabola, is x equals y squared. So I can write this in terms of y by taking the integral from, notice these are going to be y values now. So that's something that's important to be aware of. These will be y values now. So I'm going to take the integral from 0 to 2, and I need the right minus left. So this might be something that you want to write down. If I'm doing this in terms of y, I still have a lower bound and I have an upper bound, but it's going to be right minus left dy. So if I take a look at the rightmost curve, that's y plus 2. And then I'm going to subtract the leftmost curve, which is y squared. And then that'll be dy. So now my job is to integrate this. So if I integrate this, I get 1/2 y squared plus 2y minus 1/3 y cubed. And I'm evaluating all of this from 0 to 2. So I substitute things in. I get 2 plus 4 minus 8/3. And then when I sub in 0, I get 0 for all of those things. So I get 6 minus 8/3, which is 16/3 minus, 18/3 minus 8/3, which is 10/3. Notice that when I integrated this with respect to y, I got the exact same values that I got when I integrated it with respect to x. So I got 10/3. That's good. I'm supposed to get the same answer if I'm doing the same problem. So this shows us that we can also integrate with respect to y, and that might make our life a little bit easier sometimes. Number 4, find the area of the region enclosed by x equals 2 parentheses y minus 3 squared minus 1 and x equals sine of y. So this is going to be a sideways parabola with x value -1 and y value +3. It should look something like this. And then x equals sine of y is going to be a sine curve that's kind of going something like this. Now, I could do a lot better job of graphing it, but I'm just going to go and look at Desmos for the interest of time. But one thing that you notice is they don't give you any intersection points. And that means you might have to find them. So if you have to find intersection points, you may have to use a graphing utility or something of that nature. And so what I end up with here is I end up with an intersection at -0.397, comma 3.549. And I also have another intersection at 0.898, comma 2.026. So notice these functions are in terms of y. Let's check to make sure that this is actually the most efficient way to do this. And if I look at this, if I'm going right minus left, notice that my right curve never changes and my left curve never changes. So this is actually probably the best way to go about this. So I'm going to integrate from my lower bound, which is going to be a y value, remember, and my upper bound, which is also a y value. I'm going to choose y values in this case because all my functions are in terms of y. So that's from 2.026 to 3.549. Now, one thing that I'm going to make clear is that on the AP exam, you will be expected to keep more values than that if you are integrating, because remember, you are only allowed to round your final answer to 3 decimal places. Everything else you must keep. So you will have to store values, which is a objective in Honors Algebra 2 and Honors Pre-Calculus. You need to learn how to store values. And so when you find these intersection points, and I'll show you how to do it on the TI-84 in the next problem, you have to store those values and then use it in your integral if you're going to integrate using a calculator method. So my rightmost curve in this problem is sine of y. And then I'm going to subtract my leftmost curve, which is 2 times y minus 3 squared minus 1. And I'll do all of that in terms of dy. When I substitute that in the calculator, I get 1.275, and I rounded that to 3 decimal places. So that is number 4. Notice that that gives me this area by right minus left. Number 5, find the area of the region enclosed by these 3 values, or these 3 curves. So if I take a look at this, I can do this in 2 different ways, and I'm going to show you both. Since all these are in terms of x, that might be the first thing I want to look at. But if I look at these functions in terms of x, what I'm going to end up with is I have one set, which is the integral from -1 to this x value, which I will show you how to find on the calculator. Actually, let's do that right now. So if I graph this, this is what it ends up looking like. Now I want to find these intersection points. Just a reminder that we go to second calc, intersect, and you want to find the intersection points. I get 1.2148623 as my x value and 1.793003715. There's another 15 on some of the TI calculators that you can get. Just a reminder that you might want to store these values, or you can just type or write them down on your paper and then type them in. But if I'm integrating this on the calculator, I'm going to go to fnint, and I'll show you how to do that in a second. But one thing that you will notice is that if I'm integrating this in terms of x values, I have this red shaded area that I've already got. So that's from -1 to 1.2148623. And that's top curve. So root x plus 2 minus x cubed dx. Then I have to add that to this other integral, top curve minus bottom curve. And so that's root x plus 2 minus negative root x plus 2. So notice it's just 2 halves of the same sideways parabola. So minus a negative turns it into a positive. And then that's going to be from -2 to -1 in terms of my x values. So I would do all of that calculation. That's probably not the recommended way of doing this problem, because if you notice, these two are really 2 halves of the exact same parabola. So I can write this as y squared minus 2 equals x. And then I can also write the other curve as x equals y to the 1/3. And so I can end up doing this in an alternate way, which is a lot easier than all of this over here. So what I would do is I would write the integral from, notice these are now y values. So if I'm going from -1 to the y value, that's 1.793003715 of y to the 1/3. Notice that's the rightmost curve. And then if I want to go to the leftmost curve, that leftmost curve is always y squared minus 2. So I'm going to now integrate that on the calculator for you. This should end up being about 4.215 when we do it. So let's double check and make sure that we get it right. So I'm going to go from -1 to my y value of 1.793003715. And that is, I can use x or y as long as I'm consistent here. So that's y to the 1/3 minus parentheses y squared minus 2 dy. So if I do that, it thinks for a little bit, thinks for a long time, thinks for a lot longer than it's supposed to, and we end up with 4.215.